When looking at the experiments leading to our understanding of the atom, we want to be aware of the contributions made by Thomson, Rutherford, and Millikan. In each case, we want to know the scientist, how the experiment worked, and the significance of the experiment. The scientist and the significance, J.J. Thomson was involved with investigating cathode rays, and by measuring a ratio of their charge and mass, he's credited with discovering the first subatomic particle, the electron. Rutherford was studying alpha particles, and his understanding and his experiments led to a nuclear model of the atom. Millikan's oil drop experiment was used to determine the charge of the electron. So on the screen here, these are the different scientists and the significance of their experiments. Two of them were investigating electrons, both J.J. Thomson and Robert Millikan. So in this video, let's look more closely at how their experiments worked. When we look at the contribution of J.J. Thomson, as described within Atkins, the era that we're interested in, late 1800s, right around 1900s, looking at the internal structure of the atom. That means subatomic particles. He was investigating cathode rays. These are rays that are emitted when you have a potential difference applied between two metal electrodes in an evacuated glass tube. That's what that's set up here on the left. The image on the right is from the textbook. One of J.J. Thomson's experiments was to deflect this beam by applying an electric field. Atkins notes that Thomson showed that cathode rays are streams of negatively charged. What does he mean, negatively charged? Well, he's controlling the electric field, and based on the direction in which they're deflected, he can infer that they're negative because they're moving towards the positive plate. Atkins goes on to say that these were negatively charged particles from inside the atoms. This is more contentious. It wasn't clear based on the simple deflection that they were particles. Were they particles, some kind of electromagnetic wave, or some other types of energy? Even more contentious is this claim that they were particles coming from inside the atoms. My comment, are you serious? By simply deflecting the beam, that would be sufficient evidence to say they were subatomic particles? It was not. So I think Atkins is overstating the case here. He shows a picture of J.J. Thomson, the apparatus, and notes that there's two parts to it, an electric field and a magnetic field. Within that apparatus, then, Thomson is able to measure a value including a ratio of the charge and mass. E is the charge of the electron, M is the mass. So J.J. Thomson is measuring a value of the charge and mass. Atkins goes on to say that the values of the charge and the mass themselves were not known until later on, most notably by the work of Millikan. So instead of simply having a ratio, Millikan's able to carry out experiments to determine the charge alone. I'm going to call foul here on Atkins. This isn't true. J.J. Thomson also conducted experiments in which he independently calculated the charge and he independently calculated the mass. Subsequent experiments by Millikan were more convincing, were more precise, but to say that these data did not exist before Millikan is not correct. Here's the setup that Millikan used. So within here, he's going to be experimenting in observing tiny electrically charged oil droplets. He's going to be having an electric field and the force of gravity involved. And the oil drops are going to contain different increments of electrons. And he's going to take that smallest increment of charge to be the charge of an electron. Let's look more closely at these experiments. So here's a description of a cathode ray experiment. So the beam is going, in this picture, from left to right. There's a fluorescent screen that is like the detector so we can observe that beam. One thing that they found could happen would be you could deflect it in a magnetic field. Other experiments to learn more about them, here's one of the era. They're being directed at this pinwheel, which causes it to be propelled. When they change the direction of the beam, it's propelled in the other direction. So one thing that they did was to put different objects within this cathode ray tube. Here's what J.J. Thomson was up to. So this left part, this is where the beam is being generated, going from the cathode to the anode. It's extending after the anode into this part of the chamber. And in this part of the chamber, I see electrically charged plates, I see a magnet, and I see a screen to detect where the beam is striking. By the balancing of the electric and the magnetic force, he's able to calculate the charge to mass ratio of the electron. This is what's going on. So same kind of depiction. Our cathode rays are going from left to right because we have an electrical potential difference. If you first turn it on, you'd have the beams traveling in a straight line. If you turn on electric field, you can deflect the beam. So now it's on a different path. It's negative. It's being pulled down towards the positive plate. Let's also turn on a magnetic field. So we're going to turn the dial on the magnetic field and have the strength of the magnet such that the beam is now traveling once again in a straight line. It's traveling in a straight line because there's an electric field causing it to go in one direction, and that's being balanced by a magnetic field. They're equal and opposite. Now if you turn off the electric field, it's going to continue on an arc upward because it's being pulled that way by the magnetic field. Also acting on the beam will be a centripetal force. Same kind of force you might experience when you're taking a turn in a car. So J.J. Thomson is going to use this information to calculate a ratio involving the charge and the mass. There are three different forces in play: magnetic force, centripetal force, and electric force. He has turned the dial so all of these are equal to each other. I show a description, the equation for magnetic, centripetal, and electric force. A lot of different variables here, but I think many of them you're already familiar with. V would be the velocity, mass would be m, the radius, which corresponds to the arc that this is traveling on. What's I think beautiful about this is it shows the value of SI units. All of these are expressed in the SI units. Velocity involving meters and seconds. Charge is in something called coulombs. I don't see coulomb listed as an SI unit because that's expressed in terms of the ampere and second. The amount of current for the amount of time gives you the charge in coulombs. Same thing if you see here for the magnetic field strength and electric field strength. All of these fit together. All of these cancel because they're all in the SI units. Measured quantities within the experiment. He's turning the dial and can adjust the magnetic field strength, the electric field strength, and can measure the pathway, the radius. So I show in red the measured quantities. Now if we manipulate those, a little algebra, if we put these two forces being equal to each other, we'd see that the charges cancel, Q cancels, and a ratio involving the electric field strength and the magnetic field strength will tell us the velocity of the beam. Now since we have the velocity, let's take these two expressions. The only unknowns remaining are the charge and the mass. We can't determine those independently, but we can solve for a ratio involving the charge and the mass. And this is what J.J. Thomson did. Here I show some of his actual experimental data from an interesting book by Steven Weinberg. So these would be the actual experiments where he's showing data for the electric field, the magnetic field, the extent of the deflection, calculating the resulting velocity, and a ratio involving the mass and the charge. Weinberg notes, the last column shows reasonable consistency. Even when the gas and the cathode material were varied, and the velocity varied by a factor of almost 2, the mass to charge ratios came fairly close in all cases. This was, at least to Thomson, convincing evidence that cathode rays consisted of a single kind of particle with a unique value of mass and charge, independent of the cathode ray from which they were emitted. Notice the different types of experiments. He's changing the metals that were involved. He's changing the gas that was in the tube. By adjusting the potential difference, he could change their velocity. And in each case, he's looking then at the overall ratio involving the charge and the mass. So take a second, see if you can answer these questions. Stop the video and see if you can respond to these different questions involving what does it mean to see that a particle is being deflected. Share your answers. Okay, looking more at Millikan's oil drop experiment. Here's the description that's shown within the Atkins textbook. Here's another schematic, same kind of features. In both cases, we begin with having oil drops that are in a fine mist. They would fall downward. You could observe them through a microscope. You could also introduce X-rays, which are going to have them acquire a negative charge. And notice there's electrically charged plates that would allow the scientist to manipulate and suspend the drops. Millikan adjusted the electric field and he would catch a charged oil drop. And by measuring the electric field strength and the rate at which it fell, he calculated the total electric charge on the drop. Okay, how did that work? What does it mean to catch some drops and not other ones? Millikan adjusted the electric field and caught a charged drop. This is one way to think about it. So here's someone who's practicing skydiving inside, right? Gravity is pulling the person downward, and there's a stream of air that's balanced, causing the person to be suspended. So we have two different forces involved in this case, gravity pulling them downward and the air pushing them up. This balancing of different forces, that's what Millikan's going to use. So in this case, you might be able to suspend someone. If you change the object, change it to an elephant, that same force of air is not going to suspend the object any longer, the elephant any longer. So the idea is that we're going to need to balance the two forces and use information. So let's look more at the equations for that. So gravity involves mass and the gravitational constant. As that is falling downward, it's going to meet with some air resistance. So the air resistance for an object is a spherical object is described by what's called Stokes's law. The force for that includes some constants on the front and then information about the radius of the drop, the fluid it's going through, the viscosity of the air, and then the velocity of the sphere. So if someone's skydiving, initially they would jump out and they would have very little air resistance because they have a very small velocity. Eventually they're going to pick up speed, and then eventually we'll have a balancing between these two. We'll reach a terminal velocity, a constant velocity, where the skydiver is no longer accelerating. The forces are equal. Are they still falling towards the Earth? Absolutely, but they're no longer accelerating. This idea of having two different forces that we're interested in, that's what Millikan knows about. So we would have gravity and air resistance. What happens if we turn on an electric field? Well, if it's a negatively charged particle and we have it so that it can be pulled upward, now we have an electric field opposing those other two. I switch the air resistance to go in the other direction because if it's going upward, if the net force is upward, then both gravity and the air resistance are opposing it. So the air resistance can be on either side depending on whether it's going up or down. So this is how the experiment works. So when the drop is initially falling, gravity is pulling it down, air resistance is countering that. When they're equal to each other, that's when we have constant velocity. If we look at some of the internals here for the gravity, this is set up with this 4/3 pi r cubed, radius cubed. So they're taking the volume of the sphere and multiplying it by its density in order to get the mass. So that's what this term here is. If gravity involves mass and the gravitational constant, they're using the size of the sphere and its density to get its mass. The air resistance here, this is our Stokes law relationship. Same three terms. We have our radius of the sphere, the viscosity, and the velocity. So this would be the expression when the drop is falling. What if we turn on the field and have a charge and suspend, or in fact even move upward, the drops that have acquired a negative charge. We have an electric force, we have gravity, and we have the air resistance. I switched the sign here because both gravity and air resistance are opposing the electric force. So within the experiment, we've got a lot of constants. 4/3 pi is a constant, 6 pi is a constant, the viscosity of air was known, the density of the oil was known, the gravitational constant's known. So all the ones here are in blue are constants. We don't know the amount of charge, and we don't know how big the drop is, the radius of the drop. We can manipulate the electric field. That's something we can turn the dial to. And we can observe and measure the velocity when it's falling or rising. So the way the experiment would go is he would introduce X-rays in order to transfer some electrons to the oil drops from the air as the air was being ionized. He would then observe the manner in which they were falling. He would turn on the electric field to catch one that had a particular amount of negative charge that would be balanced by the applied electrical force. So he would be observing that drop, and then he would first of all observe its velocity when the drop is falling. So he had a microscope that he'd be looking through at the drop, and he would watch it go down, and he would time that. He would use that to calculate the velocity at which it was falling. The only variable in that expression was the radius. That same drop then, turn on the electric field, and now time it as it's going up. The only variable in that expression, since he's figured out the size, would be the charge. So he would take the same drop, and again, he would have it fall and time it, have it rise and time it. So the same drop he might experiment on 10 minutes, 20 minutes, again and again, in order to get a better understanding of these particular values. Okay, another opportunity. I want you to stop the video, see if you can answer these two questions. Okay, so in his experiment, Millikan's able to determine the total electric charge on a particular drop. He wants to know, is the amount of charge continuous? And if not, what is the smallest amount of charge? Can you keep having a smaller and smaller amount of charge? Or is there some finite fixed amount, the smallest amount that would be possible? So he would do an experiment and calculate a certain total amount of charge on that oil drop. Another experiment had less charge. Another experiment, and he would keep collecting data like this. So based on what you see right here, is the amount of charge continuous? If not, what's the smallest amount of charge? It's not clear to me as it's like this. Okay? I see different values, but does that mean there is some smallest increment? So he collects more data. He collects more data and then he sorts them. So he sorts them here where this would be a drop with the most amount of charge. These have similar, and these would be the least amount of charge. It's all stacked up this way. It looks like a staircase. It looks like a staircase where we can see that set increment again and again to go from one stair to the next. That seems to be the smallest amount of possible charge. And that's what he does. So it's fit here, the total amount of charge. He thinks that that means that you have different numbers of these elementary charges. You're adding an electron in each of these steps. And using modern data, the smallest amount of charge, 1.602 times 10 to the minus 19th coulombs. And the mass of the electron is then found to be more than 2,000 times smaller than that of hydrogen. Last one for you to try. Here's two questions. This first one involves looking at some data and considering how is this related to the manner in which Millikan was analyzing it. See if you can give that a try and explain it and share your reasoning.